Isn't it amazing how ideas from completely different fields can sometimes line up perfectly? It's like finding out the recipe for your favorite cake also explains how a volcano works. Well, today we're going to explore one of those surprising connections. We're going to look at the world of high finance and the world of high altitude flight. On one side, we have the sharp economic ideas of Daniel Fraga, a thinker known for his strong opinions on careful spending, fighting inflation, and the power of decentralization. On the other, we have the incredible fire-breathing heart of modern aviation, the jet engine. You might be thinking, Bill, what could a financial guru and a jet engine possibly have in common? It's a great question, and the answer is more fascinating than you might think. At first glance, economics seems to be all about money, markets, and human behavior. Jet engine engineering, meanwhile, is about physics, materials, science, and controlling incredibly powerful forces. One is about spreadsheets and policy, the other is about thrust and thermodynamics. But if we dig a little deeper, we find they are both fundamentally about the same thing: efficiency. They are both quests to get the most output from the least input, to avoid waste, and to build stable, resilient systems that don't catastrophically fail. It turns out that the principles Fraga championed for a healthy economy are almost a perfect blueprint for building a better, safer, and more efficient jet engine. Throughout this exploration, we'll use some simple economic terms that Fraga often discussed, like spending, waste, balance, and stability, and see how they map directly onto core engineering concepts. We'll see how an engineer's battle against aerodynamic drag is just like a government's fight against wasteful spending. We'll discover how the dangerous runaway heat inside an engine mirrors the destructive power of economic inflation. By drawing these fun and clear parallels, we can gain a new appreciation for both the complexities of our economies and the genius of the machines that carry us across the sky. It's a journey into how sound principles, whether for money or for machines, lead to success. So, buckle up. We're about to take off on a unique intellectual flight where finance explains physics. We'll see how Fraga's advocacy for transparency is reflected in the advanced sensors that monitor an engine's health in real time. We'll even connect his ideas on decentralized systems like Bitcoin to a revolutionary new concept in aircraft design called distributed propulsion. By the end, you'll not only understand the basics of jet engine efficiency a little better, but you'll also see that the logic of building a strong, sustainable system is a universal language spoken by economists and engineers alike. Let's get this show on the road, or rather, in the air. In the world of economics, Daniel Fraga was a passionate advocate for fiscal prudence. This is a fancy way of saying he believed governments and individuals should be extremely careful with their money, avoiding wasteful spending at all costs. Every dollar wasted on something unnecessary is a dollar that can't be used for something productive, like building infrastructure or investing in education. This waste acts as a constant, silent drain on an economy's potential. In the world of aerospace engineering, there is a perfect parallel to this concept: aerodynamic drag. Drag is the force of air resistance that pushes back against an airplane, and it is the engineer's number one enemy. It is, in essence, pure, unadulterated waste. Every bit of drag requires the jet engines to burn more fuel just to maintain the same speed, which is the aeronautical equivalent of wasteful government spending. Engineers work tirelessly to minimize it. They call one type of it parasitic drag, which comes from things like antennas, rivets, or any surface that isn't perfectly smooth. Think of these as the unnecessary expenditures in a national budget, costs that add up to a massive drain on resources. Just as Fraga would argue for trimming these fiscal parasites, engineers spend countless hours in wind tunnels smoothing out every surface of an aircraft to achieve a clean, efficient shape. The goal is to make the plane as slippery as possible, allowing it to glide through the air with minimal effort. Achieving this smooth, undisturbed airflow known as laminar flow is the holy grail of aerodynamics. When air flows smoothly over a wing, it creates lift efficiently with very little drag. This is the aeronautical version of a perfectly balanced budget, where every resource, in this case the air itself, is used to its maximum potential without creating wasteful turbulence. It's like an economy where money flows smoothly, investments are smart, and there's no inflation eating away at people's savings. Fraga might have called this economic deflation in a positive sense, getting more value for your money. For an engineer, achieving laminar flow means getting more flight for your fuel. Ultimately, the connection is crystal clear. Fraga's lesson on saving resources is a direct echo of the engineer's relentless battle against drag. Whether you're managing a nation's finances or designing a multi-million-dollar aircraft, the core principle is identical. Waste is the enemy of progress. Eliminating it requires discipline, attention to detail, and a deep understanding that small inefficiencies, when multiplied, can lead to massive losses. By designing aircraft that slice through the air with minimal resistance, engineers are putting Fraga's economic philosophy into practice, ensuring that the precious energy stored in every drop of jet fuel is spent on moving forward, not on fighting unnecessary battles against the wind. If drag is like wasteful spending, then the heat inside a jet engine is like economic inflation. Daniel Fraga famously warned about the dangers of uncontrolled inflation, where a central bank prints too much money. At first, it might seem like a good thing. More money flowing around can create a temporary economic boom. But soon the value of each dollar plummets, prices spiral out of control, and the entire system becomes unstable and inefficient, potentially leading to a total collapse. In a jet engine, the single most important factor for power is heat. The hotter the gas exiting the engine, the more thrust it produces. But just like inflation, too much heat or heat that isn't properly controlled can lead to catastrophic failure. Engineers are constantly trying to increase the thermal efficiency of an engine, which is a measure of how well it converts the heat from burning fuel into useful work. One way to do this is by increasing the pressure ratio inside the engine, governed by a principle called the Brayton cycle. By squeezing the air more tightly before adding fuel, the engine can burn that fuel at a much higher temperature and pressure, extracting more energy. This is similar to a central bank carefully managing economic growth. A little bit of controlled growth is good. However, if engineers push the pressure and temperature too high without reinforcing the engine's components, they risk disaster. The metal parts could melt or fracture under the stress, just as hyperinflation can fracture an economy. This delicate balancing act is the core challenge of modern jet engine design. Engineers want the benefits of high temperatures, more power, and efficiency, without the destructive consequences. They are in a constant battle against engineflation. To manage this, they use incredibly advanced materials like single crystal turbine blades grown in a lab that can withstand temperatures hotter than the melting point of the metal they're made from. They also design complex internal cooling systems which use air from the compressor to create a thin protective layer of cooler air over the hottest parts of the engine. This is like a government implementing smart policies to protect citizens from the worst effects of inflation. So when you see a jet engine, think of it as a tiny, self-contained economy where heat is the currency. Fraga's warnings about the perils of printing too much money resonate perfectly with the engineer's challenge of managing thermal energy. Both systems require a masterful balance. Push too hard and you get a powerful but short-lived boom followed by a spectacular failure. Manage it wisely with strong materials and cooling safeguards, the equivalent of sound fiscal policy, and you create a system that is not only powerful and efficient, but also stable and reliable for the long haul. Taming the heat is taming inflation, a principle that holds true both on Wall Street and at 30,000 feet. Let's dive deeper into the heart of the engine, the combustion chamber. If the engine as a whole is an economy, then the combustion chamber is its central marketplace, a place of high stakes, high-speed transactions where the fundamental laws of supply and demand play out in milliseconds. In any economy, you have suppliers who provide goods and services and consumers who create demand for them. A healthy economy keeps these two forces in a delicate balance. In the combustion chamber, the supply is the massive volume of highly compressed air delivered by the engine's compressor section. The demand is created by the fuel system, which injects a fine mist of kerosene into that super-pressurized air. The goal is to achieve the perfect air-to-fuel ratio. If you inject too much fuel for the amount of air available, so excess demand, you get an inefficient, smoky fire. This is like an overheated economic boom fueled by cheap credit, where too much money chases too few goods, leading to waste and instability. In an engine, this condition can cause the flame to become unstable or even extinguish itself entirely, a dangerous event known as a flameout. On the other hand, if you inject too little fuel for the air, insufficient demand, the fire will be weak and may not produce enough energy to keep the engine running. Kinda similar to an economic recession where a lack of spending brings commerce to a halt. Engineers refer to the ideal mixture as the stoichiometric ratio, but we can think of it in Fraga's terms as the gold standard of internal combustion. It's that perfect stable point where every molecule of fuel is matched with the right number of oxygen molecules to achieve a complete, clean, and powerful burn. Modern engines use sophisticated computer systems called FADECs, Full Authority Digital Engine Control, to constantly monitor conditions and adjust the fuel flow with incredible precision. These systems act like a hyper-aware central bank, making thousands of micro adjustments per second to maintain that perfect balance, ensuring the engine performs efficiently, whether it's idling on the tarmac or at full throttle climbing through a storm. This constant dance between air and fuel highlights a core economic principle that Fraga would appreciate. Balance is not static, it is dynamic. A healthy system, whether economic or mechanical, must be able to adapt to changing conditions while maintaining its core equilibrium. The combustion chamber is a testament to this idea. It's not just a simple fire pit. It's a meticulously engineered environment designed to manage a continuous controlled explosion. It's a high-speed ballet of supply and demand, where achieving the perfect balance isn't just a goal for efficiency. It's absolutely critical for survival. One of Daniel Fraga's most forward-thinking ideas was his strong advocacy for decentralization. He was an early proponent of cryptocurrencies like Bitcoin, seeing them as a way to create a more resilient and transparent financial system that wasn't dependent on a single point of failure, like a central bank or government. In a decentralized system, power and control are spread out across a network. If one part of the network fails, the rest can continue to operate. This creates a system that is inherently more robust, adaptable, and resistant to shocks. It's a powerful idea, and amazingly, it's now taking flight in the world of aviation through a concept called distributed propulsion. Now, traditionally, aircraft have relied on a small number of very large, centralized jet engines, usually 2 or 4, slung under the wings. This is a simple and effective design, but it's like having an economy that relies on just 1 or 2 major industries. If one of those massive engines fails, it creates a significant problem that requires the entire aircraft system to compensate. Distributed propulsion flips this idea on its head. Instead of a few large engines, the aircraft uses many smaller, lighter, and often electric motors distributed across the surface of the wings or fuselage. This is the aeronautical equivalent of Fraga's decentralized economy. The benefits of this decentralized approach are enormous. First, it dramatically improves efficiency. By blowing air uniformly over the wing's surfaces, these smaller motors can increase lift and reduce drag, allowing the aircraft to fly using significantly less energy. Second, it enhances safety and resilience. If one or even several of the small motors fail, the impact on the aircraft's overall performance is minimal. The remaining motors in the network can easily pick up the slack, making the system far more fault tolerant than a conventional design. This is precisely the argument Fraga made for decentralized finance. A network of many small participants is stronger and more stable than a system dominated by a few large, too big to fail institutions. This parallel shows how a fundamental principle that decentralization builds resilience can be applied to solve problems in vastly different domains. Fraga saw it as the future of money, a way to protect individuals from the whims of centralized control. Aerospace engineers now see it as the future of flight, a way to build aircraft that are not only more fuel efficient and environmentally friendly, but also fundamentally safer. Whether you're designing a currency or an airplane, spreading out the workload and eliminating single points of failure is a powerful strategy for building a system that can withstand the unexpected and thrive in a complex world. Daniel Fraga often argued that transparency is the bedrock of a trustworthy system. He believed that for an economy to be fair and efficient, all the information about spending and resource allocation should be open and accessible. Without clear, real-time data, it's impossible to make good decisions, spot problems before they become crises, or hold leaders accountable. In the high-stakes world of jet engines, this call for transparency is not a political philosophy. It's an absolute necessity for safety and performance. This is where modern engine diagnostics come in. An engine doesn't just run, it constantly reports on its own health with total transparency. A modern turbofan engine is equipped with hundreds of sensors that monitor everything from temperature and pressure to vibration and rotational speed. This data is streamed in real time to the cockpit and to maintenance crews on the ground. This constant flow of information provides a perfectly transparent view into the engine's inner workings. It allows pilots and engineers to spot tiny anomalies, a slight increase in temperature here, a minor vibration there, long before they can develop into serious problems. This is the engineering equivalent of a transparent government budget. With all the data out in the open, you can ensure the system is operating as designed and allocate resources. Like maintenance, exactly where they are needed most. Beyond transparency, Fraga also emphasized the importance of wise investment. He argued against malinvestment, spending money on things that don't provide a good long-term return. Instead, he advocated for putting resources into high-quality assets that create lasting value. Engineers face this exact choice when selecting materials for an engine. They could use cheaper, heavier metals, but that would be a classic malinvestment. The initial savings would be quickly erased by higher fuel consumption and lower performance. Instead, they make a wise investment in exotic high-performance materials like titanium composites and nickel-based superalloys. These materials are incredibly expensive and difficult to manufacture, but they offer an enormous return on investment. The turbine blades at the heart of the engine, for example, are often made from a single crystal of a superalloy. They are lightweight, incredibly strong, and can operate in temperatures that would melt steel. The weight saved and the heat resistance gained directly translate into massive improvements in fuel efficiency and engine lifespan. Using cheap materials would be like a government printing unbacked money. It might seem like a solution in the short term, but it inevitably leads to a crash. Fraga's principles of transparency and wise investment are therefore built into the very DNA of a modern jet engine. Finally, let's talk about stability. Daniel Fraga consistently argued that the goal of any economic system should be to create a stable and predictable environment where businesses and individuals can plan for the future with confidence. Wild swings, market shocks, and policy uncertainty create fear and paralysis, grinding progress to a halt. This emphasis on stability is paramount in jet engine operation. An engine doesn't just have to perform well under ideal, steady conditions. It must remain stable and reliable through every phase of flight, from the turbulent climb to the smooth cruise, and it must be able to withstand sudden, unexpected market shocks. In aviation, these shocks can come in many forms. A sudden gust of wind can disrupt the airflow into the engine. While flying through a flock of birds, a bird strike can cause severe damage. An abrupt change in throttle can create a pressure surge inside the compressor. Any of these events can lead to a dangerous instability known as a compressor stall or surge. This is when the blades inside the compressor stop biting the air correctly, causing the flow of air to break down or even reverse. It's the engine's equivalent of a stock market crash or a fiscal stall, where confidence collapses and the entire system violently shudders to a halt. To prevent this, engine control systems are designed to be the ultimate stabilizers. The FADEC, which we mentioned earlier, acts like a vigilant central bank, constantly monitoring the engine's operating conditions. If it detects the slightest hint of instability, it instantly makes microscopic adjustments to fuel flow, guide vanes, and bleed valves to keep the engine within its stable operating margin. It anticipates problems and corrects them before they can escalate. This is precisely the kind of proactive, stabilizing policy that economists advocate for to prevent financial panics. The goal is to maintain confidence in the system, ensuring it can absorb shocks without failing. In conclusion, the wisdom of Daniel Fraga provides us with a surprisingly effective lens through which to understand the marvels of modern engineering. His principles, fiscal prudence, inflation control, balanced supply and demand, the resilience of decentralization, the necessity of transparency, and the pursuit of stability are not just abstract economic theories. They are the very same principles that engineers apply every day to design, build, and operate the jet engines that power our globalized world. Thinking like Fraga doesn't just help us build a better economy, it helps us build better, safer, and more efficient machines. It reminds us that whether we are managing money or manipulating fire and air, the quest for a smart, stable, and waste-free system is a universal one.